Okay, let's pick up where we left off here on assessing body composition. So we're going to go over three different methods. We're going to go over densitometry, skin fold thickness, and biological impedance analysis. So the way densitometry works is that you have your body density divided by your body mass equals your body volume, right? So a density of an object is quite simply how much mass it has compared to how much volume it has. So think about those little shipping peanuts that you used to cushion items in boxes and things when you ship them. Uh, they have a relatively low amount of mass to the volume, right? They don't weigh very much for how big they are. Whereas if you had a same piece of lead that size, it would have a much higher mass per unit of volume, so it's more dense, right? It just weighs a lot for its size. And the thing is that basically fat is not very dense, right? Fat is not dense, so the more fat you have, the less dense you are. So the way we do this is we measure your body mass on a regular scale. We just take your weight on a scale. And then we measure you under the water. Okay, we measure you under the water, and basically the principle is that your fat floats and the rest of you sinks. So when we measure in the water, we also have to account for the water density, which should be 1.0 grams per centimeter cubed. That's the standard for the density of water. In fact, our whole metric system is based on that. We got to account that for the air trapped in your lungs because you're not going to get it all out, and the air in your lungs is going to make you float. So if we don't account for that, then we're going to misestimate your body fatness. So here's a picture of not quite that slide just yet. So we're going to look at two men in the water, right? Okay, both of these guys, Jack and Dave, both weigh, they're both 74 inches tall, right? 6'2". They're both 205 pounds. Now, if we look, Jack over here, he's kind of buff and fit, right? Nice little skinny waist there. Looks like he works out for sure. He weighs 6.5 kilograms underneath the water. That's about 16 or so pounds, right? His buddy Dave over here, Dave's not really fat, but he's a little soft around the middle, right? Not as buff as Jack. He weighs only 5 kilograms under the water. Now, outside the water, these guys both weigh the same, right? They both weigh the same. But Dave weighs less because he floats more because his fat floats, all right? So that also means that he has a greater volume, right? He's bigger. He weighs 205 pounds, but he's bigger. He takes up more space, has more body volume than Jack, who's all buff, right? Because the fat, per pound of fat, takes up more space than a pound of muscle, right? So he is not as dense. He is 1.057 grams per milliliter, and Jack is 1.075 grams per milliliter. And that might not sound like a big difference, but it's enough to where Jack has 10.5% fat and Dave has 18% fat, right? So if we look at the fat weight of the two men, Jack has 21.4 pounds of fat, Dave has 37.7 pounds of fat, right? So Dave has almost 1.5 times as much fat, approximately 1.5 times as much fat, almost twice as much as Jack here, right? So that's how we can use underwater weighing to tell how fat somebody is. And the thing is, these guys both have the same body mass index. If we did a body mass index on these guys, they're exactly the same, right? But one of them's fatter, Dave is fatter, and Jack is fitter. Okay, so the problem with this is we have inaccuracies in the system due to a variation in the density of the fat-free mass, right? So our fat mass, we know what the density of that is. That is 0.9 grams per centimeter cubed, and that is going to be the same on everyone. Everyone, their fat mass is the same density. Their fat-free mass, however, could be different. We assume that it's 1.1 grams per centimeter cubed. And the problem is that is not always right, okay? So your fat, basically, the density of water is 1.0, right? The density of your fat mass is 0.9, so that means it floats. The rest of you sinks, but we don't know exactly how much of you sinks. We can get a pretty good idea, and 1.1 grams per centimeter cubed is pretty good, and it's going to be pretty accurate most of the time. But the problem is that, as you see here, very small differences in density make a big difference in how fat, in body fatness, right? The other problem is that we can have problems with inaccuracies of measuring the air trapped in the lungs. Maybe we didn't measure the air trapped in the lungs properly. Maybe the person didn't get all their air out. I can tell you after doing hundreds of these that's one of the problems is people don't always get all of their air out. And for the air that they don't get out, that makes them float. And if you float, you're going to be less dense, and we're going to overestimate your fat. Okay, so this is what it actually looks like when you do it. All these pictures look like they're from the 70s or early 80s because they are that old. These are from an old professor of mine, right? Basically, they've all already weighed this fella outside the water, and now they're just weighing him in the tank of water. It can also be done in a swimming pool, right? So we just know what his weight is in the swimming pool when he's completely submerged, and we can put that into our calculation. Okay. Another method for assessing body fatness is biological impedance analysis. So with this, you put a very small voltage through the body. The general principle of this is that electricity flows very well through the water in our body, but it does not flow well through the fat, right? It flows right through the water. So what it does, it tells what our total amount of body water is, okay? And we know that fat-free mass is 73% water. So if we know how much water we have, we can tell how much fat-free mass we have. And the rest has got to be fat. So let's say we do this bioelectrical impedance analysis on someone. We know that they have that they weigh 100 pounds and that 90 pounds of that is fat-free mass. Well, the other 10 pounds has got to be fat. That's all it can be. And that's basically how this works. Now, the problems with this is that we work with some assumptions. One, the mathematical calculations assume that the body is a perfect cylinder, just like a tube. But obviously, your body is not a perfect cylinder. It also assumes that the participant is properly hydrated. If you're dehydrated, it could definitely mess up these results. This is a picture of the old systems of how it used to be done. It would shoot this low level of electricity from your foot up to your hand and measure the amount of resistance it encountered all the way up there. Now, keep in mind that this level of electricity is so low you can't feel it. You don't even feel a slight little tingle. You don't feel anything. Okay, here's one of the newer systems. This is a handheld system. This one, instead of going from your foot to your hand, it just goes from one arm to the other. They also make body fat scales. You've probably seen them. You can buy them at Target or the drugstore or Walmart, where you just stand on them and it shoots it from one foot to another. And you might think to yourself, well, you know, it's shooting from one foot to another, but I carry my weight up top and my body fat up top. So is this really accurate? And basically, the short answer is yes, it is just as accurate. It doesn't matter whether it goes hand to hand, foot to foot, or hand to foot. Like the old systems, they're all equally accurate. And because of technology, what used to be this big and have all these wires hooked up to it can now be this small. Okay, now we're going to talk a little bit about skin folds, right? So a lot of people have probably had skin folds done in the gym. This is what it looks like. You pinch body fat at different places on your body. Okay, and so what they do is they pinch the body fat on different places on your body, and they come up with the sum of the skin folds. They add up the skin folds from different sides. For women, usually it's tricep, iliac crest, and thigh. So that's the tricep. That's iliac crest is your hip bone, so it's right on your hip, and then your thigh. For men, it's usually chest, abdomen, and thigh. And the three-side equation is the most popular because they've done some studies to show that it is just as accurate as doing 7 sides. So if you can do 3 or you can do 7, you might as well only do the 3, right? So then what we do is we add all these skin folds together. We add the tricep, the iliac crest, and the thigh, or the chest, abdomen, and thigh. We get what we call the sum of the skin folds, right? Sum just means you've added them together. And we put them into equations. And I'm going to end this video right now, and then when we're done, we will talk briefly about those equations.